What's up, guys? Welcome to session 3 of Introduction to Linux Bash Scripting. As always, I am your instructor, Kevin Downs. Let's go and get started here. So in our third session here, we're going to be going over shell programming. In our last session, we went over input, output, redirection, and pipes, command separation and grouping, background execution, file name expansion, shell variables, command substitution, quoting and escaping meta characters, fish shell features, command execution, and startup files. Today, we'll be going over shell script features and capabilities, creating and running a script, working with variables, environmental variables, working with data types such as formatting, base conversion, and setting special attributes, and input-output techniques, conditional constructs such as if-then and else-if, looping constructs such as for, while, until, and basic operators. Let's go and get started with some shell script features and capabilities. So in shell scripts, you can use wildcard substitution and file names, background processing, command aliasing, command history, file name substitution, input and output redirection, piping, and shell variable substitution. So the things we can do in bash and normal command line, we can also use in our scripts. So why use bash scripting? Well, it's good for orchestrating system startup shutdown tasks, automatically renaming collection of files, finding all duplicate MP3 files on a hard drive, or other duplicate files. It doesn't have to be MP3 files. Orchestrating a suite of tools for tracking a password database, or a suite of tools. Finding weasel words in your writing, okay? And guys, weasel words just means finding specific words in like your script or your files, okay? So that's just a phrase. Implementing a relational database out of text files, and simplifying configuration and reconfiguration of software. So in order to create and run a script, we'd have to open the terminal, go to the directory where you want to create your script, create a file with the .sh extension. And guys, this serves two purposes. One, when we put .sh at the end of the file, it tells everyone else as well as yourself that this is a script file. And when we open an editor such as Vim, by using this extension, it actually opens up other features that are only available to a shell script. Okay. So next we would write the script in a file using editors such as Vim. We would make the script executable with the command chmod plus x and then the script name. And then we would run the script using the / file name. Or if this script is contained somewhere else besides our current directory, we would give the full path right here, okay? Not just /. / says, look in the current directory I'm in and run this, okay? So guys, take note in the last step, just as I mentioned, the path of the script is used, or the full path is used if the script is in another directory, okay? So an example of this, guys, I want to create a script called hello.sh, so I would do vim space hello.sh. I would put my hash playing at the beginning here. Okay. And this hash playing, guys, tells the loader what interpreter to use. Okay. We could do /bin /k shell /fish shell or any other shells we'd like to use. This is always the first thing that's put in our shell scripts. This is called the hash pling. Okay. So it's # or hashtag and then exclamation point and then the shell you're going to use, okay? And then here we have a comment, and comments are not interpreted by the interpreter. So when it sees this hashtag or #, it says, hey, don't interpret this line. We have another comment here, and we're going to say, hey, echo hello. And then once we're done with that, we'll do a right quit, and we'll do chmod plus x hello.sh to make the script executable, and then we'll execute the script. So let's talk about working with variables. This is a very important topic. So a variable is a character string to which we assign a value. The value assigned could be a number, it could be a text, it could be a file name, device, or any other type of data. So a variable is nothing more than a pointer to the actual data. The shell enables you to create, assign, and delete variables. The name of variables contain only letters, so A to Z or capital A to Z, numbers 0 to 9, or the underscore character. So by convention, Unix shell variables will have the names in uppercase. So those home and shell and user variables are always going to be uppercase. The following examples are valid variable names. So we have _ALI, token _A, var _1, and bar _2. These are all correct variable names. Here are some incorrect variable names. We have 2 _var, we have dash variable, we have var1 dash variable 2, and we have var _a exclamation point. So guys, these are not right. We can't use this exclamation point or this dash here. Okay, the dash here. All right, we can't use those things when we're doing those variables. So guys, the reason we can't use those in variable names is because these commands, such as exclamation point, star, dash, are characters that have a special meaning for this shell, right? So when it sees that, it's going to try and interpret those as the actual exclamation point or star, not a name of the file, okay? So guys, to access a value of a variable here, you would see we would say the variable. In this case, we have name. And then we would set it equal to the string XYZ. And then we would echo, and then variables always start with a $sign. And the variable name was name. And so it would spit out XYZ, right? So variables in Bash have a dual nature as both arrays and variables. So to set a variable, as we just saw, we would use the equal sign. Okay, so if we do foo equals 3, this sets foo to the number 3. But make sure, guys, that you don't put a space in between the equal sign and 3 here. So if we do that below here, so we have foo space equals space 3, this actually invokes the command foo with the arguments equals and 3. So it thinks foo is a command, and now because there's spaces here, it thinks that equal sign is an argument and the 3 is an argument, okay? So make sure when you set a variable, there are no spaces. If you want to use a space, you can dip into the expression sublanguage that exists inside double parentheses. So here we can do double parentheses, and we can do foo space equals 3, okay? And that will actually set foo to 3. Okay? And just as we've been seeing, to reference a value of a variable, you use a $sign, right? So when I do echo and I want to echo the value of the variable foo, I have to put that $sign there so it knows that this is a variable. We can also delete a variable or unset it. So if I say foo equals 42 and I echo foo, it's going to say 42. Well, I don't want that to equal 42 anymore, so I do unset is the command, space, and foo is the variable name. And now when I do echo foo, it's going to print nothing, right? Because I unset that variable. We can also set one variable equal to another. So here I can say foo equals the variable bar. And this will assign the value of the variable bar to foo. If you want to assign a value which contains spaces, be sure that you quote it, guys. So this is wrong here. We say foo equals x space y space z, okay? This is actually going to set the foo variable equal to x, and it's going to actually try to execute y on z, okay? The right way to do this is foo equals quotation mark xyz with spaces in between, and that will actually set the variable foo to x space y space z. And sometimes, guys, it's actually necessary to wrap a reference to a variable in braces, such as we see here. We see echo $sign. We have some curly braces, okay? And then the variable foo, okay? And that's important. We're going to see some examples here shortly about why that's important. So there are some special bash variables for grabbing arguments to scripts and functions, okay? So echo 0 prints the script name, so variable 0. Variable 1 prints the first argument, 2 the second argument, all the way up until 9. So 3, well, third, fourth, etc. All the way up until 9. And then at 10, this actually prints the first argument followed by 0. So what we have to do for these only, we have to actually cover it with these curly braces so that it prints the 10th argument, right? And then we have the $sign, hashtag, or £, which prints the number of arguments, okay, which we'll see later. So it is possible to write arithmetic expressions in Bash, but you have to use some caution when you're doing this, guys. So we can use the command expr or expression, which prints the results of arithmetic expressions, but one must take caution, just as we said. So expression 3 plus 12 will print 15, but expression 3 times 12 will probably, not always, but probably crash, and it's going to try and expand to all files. So what we'd actually have to do is we have to do expression space 3, we have to do a backslash, and guys, this backslash is an escape character. This tells the command line, hey, whatever comes next, don't interpret as a command, okay? Take it as it is, all right? So in this case, it would be multiplies, and this will actually multiply 3 by 2, or 12 now, which would come out to 36. A much better way to do arithmetic, guys, is this double parentheses here, okay? It's a much more forgiving method, so we can do x equals 3 plus 12, and what's going to happen is it's going to assign 3 plus 12 to x, so we'll give the value 15 to x, and if we do echo variable x, prints 15. Same with multiplying, 3 times 12, assign that to the variable x, we echo the variable x, and that would print 36. If you want the result of an arithmetic expression without assigning it, you can do the following format below, which is going to be $, double parentheses, and then the arithmetic inside. So this would print 15, this would print 36, okay? Let's talk about environmental variables. So environmental variables, or ENVs, basically define behavior of the environment. They can affect the process as ongoing or the programs that are executed in the environment. So let's talk about the scope of an environment variable. So scope of any variable is the region from which it can be accessed or over which it is defined. An environment variable in Linux can have global or local scope. So if it's a global variable, a global scoped variable that is defined to a terminal can be accessed from anywhere in the particular environment which exists in the terminal. So that means it can be used in all kinds of scripts, programs, or processes running in the environment bound by the terminal. So here we see export and then the variable name and the value. So this is how we set a global variable. We have to use that export option, okay, or command. Or we can do set and then the variable name and the value of the variable. So export or set command both work for that. So guys, when I do this, this means that if any user logs on to the system and they have a variable, let's say it's named foo and it equals bar, any user on the system will have that variable foo with the value of bar in it, and they can use it in their scripts or their terminal, okay? On the contrary, local variables, so a locally scoped environment variable that is defined in a terminal cannot be accessed by any program or process running in the terminal. Can only be accessed by the terminal in which it is defined. And remember, we just saw how to do that. All the previous variables we saw were all the variable equals and then the value, and that's it, right? So local variables can be accessed only on the terminal that they were set in. Global variables can be accessed on any terminal by any user on the environment. So let's move on to data types. So data types used by a kernel are divided into 3 main classes. The first is standard C types such as integer, explicitly sized types such as U32, and types used for specific kernel objects such as PID_T. We're going to see when and how each of the 3 data type classes should be used. For example, there are typical problems you might run into when porting driver code from by86 to other platforms or when linked lists are exported by recent kernel headers. This is just an architecture type, guys. This is 86 type, okay? And before I move on, I just want you to know that we're going to briefly cover these data types, and the conversions of these numbers here aren't too important for what you're going to be doing right now. You just want to have some foundational knowledge for them, okay? So we're going to look at formatting here, okay? So map to java.lang.integer, the binary representation is a 4-byte integer with the sign bit flipped, okay? So we're looking at integers here, okay? So these are going to be integers. So possible values for an integer can be 0 all the way up to this huge number right here, right? And again, this is mapped to java.lang.integer. The binary representation is a 4-bit integer matching the HBase bytes to bytes method. The purpose of this type is to map existing HBase data that was serialized using this HBase utility method. If that is not the case, use the regular sign type instead, okay? An example of that is any unassigned integer, okay, which we just saw here. It can be any number between 0 all the way up to this huge number here. We also have the timestamp data type, okay? And the format is year, month, day, okay? hour, minute, second. Okay. And this is mapped to java.sql.timestamp with an internal representation of the number of nanos from the epoch. The binary representation is 12 bytes and 8-byte long. An 8-byte long for the epoch time plus a 4-byte integer for the nanos, okay? An example of here could be any timestamp we want, okay? So I could actually, I'll just type it here. I could say like 1970, oops, sorry guys. Get back to our slide here. Press the wrong button. So I could say, you know, like 1970, oops, did it again. Oh, I know why, my number lock's off. Sorry guys, 1 second. There we go. There we go, 1970, that's the year. I could say like the month is 02, so February, and I could say 1st. I could say the 8th hour, 8 a.m., so 08, 32 minutes, and 47 seconds, all right? So that would be an acceptable timestamp, right? All right. All right, we can go ahead and talk about base conversion here, which is how to convert numeric bases within shell scripts. There are really 4 commonly used numeric bases to consider: binary, octal, decimal, and hexadecimal. So we used to work in base 10, so 10 equals 1 times 10 to the first plus 0, and 100 equals 1 times 10 to the 2 plus 0 times 10 to the 1 equal plus 0, okay? So you see we started at 2 and then 1 and we went down, okay? So that maps to other numeric bases. So 1010 base 2, our binary, is really 1 times 2 to the third plus 0 times 2 to the second plus 1 times 2 to the first plus 0, or 8 plus 0 plus 2 plus 0 equals 10, right? Octal is the same thing, so 33 base 8 converts to decimal as 3 times 8 to the first plus 3 equals 27. The long, complicated way to create a base conversion utility is therefore to disassemble every value given and apply to the transition shown. Then have an internal value that's a common base, probably base 10, and then have another routine that converts the common base to the desired output, which we kind of saw up here, right? That's the long way to do it. A much simpler way to do it is what we see here. So there's other ways to do this. For example, the BC command, which supports to users specifying both the input and output numeric base, BC. The binary calculator. It is a bit tricky to work with as it's an old school Unix command, and the most common way to work with it is the BC program is to use echo to send it to the commands needed as demonstrated here. So we can do echo, quotation mark, I base equals 16, semicolon, O base equals 2, semicolon, FEF 33 G9, single quote, space, pipe, space, BC. And we hit enter, and it will give us the representation, okay? Guys, remember semicolon is just a way to type a command on the next line. This is no different than typing this command, hitting enter, typing this command, hitting enter, and then typing this command, okay? The semicolon is just creating a new command line, okay? So let's talk about setting special attributes. So variables and parameters are used by Korn shell to store values. Like other high-level programming languages, the Korn shell supports data types and arrays. Shell variable names can begin with an alphabetical A through Z or underscore character followed by one or more alphanumeric A through Z 0 through 9 underscore characters. Other variable names that contain only digits or special characters such as exclamation point, at, pound or hashtag, percent, splat or star, question mark, dollar sign are reserved for special parameters set directly by the Korn shell. So shell variables can have one or more attributes that specify the internal representation, access, or scope, or the way they are displayed. This concept is similar to a data type in other high-level programming languages, except that in Korn shell it is not restrictive. Variables can be set to integer type for faster arithmetic operations, read-only so that the value cannot be changed. Left-right, justified for formatting purposes, and more. To assign a value and or attribute to a Korn shell variable, use the following format with typeset command. So we do the command typeset space dash the attribute we want to do, and then the variable equals to the value we want to set. Okay. Let's go ahead and talk about input and output techniques. So the bash shell has 3 standard streams in input and output direction, which we've seen before. The first one is standard input, And the standard input stream is numbered as standard in 0, and the bash shell takes input from the standard in. So by default, the keyboard is used as input, okay? And we see that here. So we see less than sign. This is standard input, and this is going to overwrite any files we have. And then we have 2 less than signs, which is standard input, and it's going to append any info we have, okay? We also have standard output, or standard out, and the standard out stream is numbered as standard out 1, and the bash shell sends output to standard out. Output goes to the display. This is what we see when we hit enter on a command. So we have the greater than sign, which redirects standard output, and this overwrites again. And we have 2 greater than signs, which redirects standard output and appends it, okay? Last one we have here is standard error. The standard error stream is numbered as standard error 2. The bash shell sends error messages to the standard error. Error messages also go to the display. So to use this, we have to do the number 2 and then the greater sign, and that will redirect errors, okay? This works just the same as the other two. 1 greater than sign overwrites and 2 appends, okay? So guys, this is similar to standard out, except this only works for errors, okay? So if I were to do, let's say, a cd to a directory named fake, okay? And that directory doesn't exist, an error is going to come back to me. It's going to say, hey, that directory doesn't exist. So if I did a 2 greater than sign, it would actually redirect that error to wherever I would like it to go, okay? However, if the directory did exist and I tried to redirect this, it wouldn't work because it's not an error, okay? So following this, guys, we're going to go ahead and start talking about conditional constructs.